Excellent. All right, so I'm still trying to figure out how this recording system works. I deleted a little bit under 2 hours of video and somehow gained 3 hours of recording time. So I'm not quite sure how that works, but I do know about how Uncountable and Countable works, so I will talk about that instead. Nobody emailed me issues about countable versus uncountable. Everybody seemed to say that they were familiar with it, so we will do the blitzkrieg view, which goes well with the question about France and effort. Countable, uncountable. So we basically say a sequence is countable if I can put it into a one-to-one correspondence with the positive integers. It's at most countable if it's finite or countable. We all know what a finite set is. It is a set that has finitely many elements. If you think this is circular, please take a physics class or a chemistry class where you describe the ideal gas law. What does the ideal gas law describe? The behavior of an ideal gas. And what is an ideal gas? A gas which obeys the ideal gas law. So you do have to work a little bit as to what the hell do we mean when we say a set has finitely many elements. So we want to basically put things in some kind of one-to-one bijection with the set of 1 through n, and that will be the set with n elements. The only set we really know exists is what? Or what's our first set? The empty set. And so 0 corresponds to the empty set. The laws of set creation, what we can do is we can form the set that consists of the empty set. And what number will this be? What number should that correspond to? 1. Now we can form another set. It's the set containing the empty set, and there's one other set we know. The set containing the empty set. And what number is this? 2. The empty set. The set containing the empty set, and the set containing the empty set, and the set containing the empty set. And this number would be? Do I need another? Yeah, probably need another brace for it. OK. If you notice, 1 is a subset of 3. 2 is a subset of 3. Each number is a subset of the number of all the numbers below. You can build up the integers nicely from this. At one point in your life, if you want to be a math geek, you should see this. If you'd like to be other kinds of geeks, come to WICMA between 6:30 and 7 and either support me or go against me. Either one is fine. So here is a way to build up the natural numbers. Okay? And inclusion is going to correspond to less than or equal to. All right? We're not going to do too much with this, but it's kind of nice to see what can be done. I'm not going to go into great detail. All right, so the integers are countable. And so the question is, what other sets are countable? So the rationals are countable. Clearly, the rationals can't be of smaller cardinality than the integers, because the integers are a subset. The only question is, are the countables the same size or are they larger? And so what I can do is I will just look at all numbers of the form m over n, where m and n are relatively prime, and m and n are greater than 0. So I'm missing the negative rationals and I'm missing 0. Well, if I can handle this case, I can easily put in 0 and I can easily put in the negatives. And what I'm doing is I will walk up in like a grid fashion like this. There's lots of different ways of doing this. So this would be 1, 1, 2, 1, 3, 1, 4, 1. This would be 1, 2, 2, 2, 3, 2, 4, 2, and so on. Now, if you look at this, I've got a bunch of numbers repeated. If I look at the ratio of this, that'll give me 1 over 1. This will give me 1 over 1. This will give me everything on this diagonal is the same. This is not the most efficient way of writing the rationals, but it's fine. It's an easy way to do. And the two standard ways to get it is I can now just walk diagonally like this along these lines, and you give me any rational number, and I know when I will get to it. Or the other path that people often do is they often do paths like this. That's fine. Or if you want to do all the rationals where you include the negatives as well, people will often spiral out like this. Lots of different ways of doing it. And an argument like this proves that the rationals are countable. You can prove lots of sets are countable. Algebraic numbers, these are numbers that solve polynomials with integer coefficients. These are countable. Not all numbers are countable. So a set of numbers that's not countable would be the reals. And the standard proof of this is Cantor's diagonalization argument. And so again, nobody emailed me that they were uncomfortable with these, so I'm going to do this really fast. So Cantor's diagonalization argument. Well, without loss of generality, it's sufficient to just look at what's going on in the interval 0, 1. If I can show there's uncountably many numbers in 0, 1, then there will be uncountably many real numbers total. And we can either look at things in base 2 or base 10. Which do you prefer? Base 10. All right. Let's do base 10. All right, we'll do base 10. So look at base 10. Assume 0, 1 is countable. So we can enumerate the numbers x1, x2, x3, xn, ... And we'll write each of these numbers in base 10. We'll write it as x, dot x11, x12, x13, ... x21, x22, x23, ... xn1, xn2, xn3, ... xnn, ... And what we're going to do is we're assuming this list is complete, that every real number in 0, 1 is included in this list. Now we've got to be a little bit careful. What do we have to be careful about? When we're writing numbers in decimal, so how would you write the number 1/2 in decimal? 0.5. So you're very minimalist today. What if you were like Charles Dickens and were being paid by the character? 0.499999999, right? We have the Dickens expansions, where we can have this infinite string of 9s, and we just keep getting more and more and more of them, right? So what we might want to do is we might want to say, if we have two different ways of writing a rational, let's choose the one that terminates. Or what else? Maybe put them both in.
Or couldn't you just have like 5000000?
Well, that's saying choose the one that terminates,
Okay.
right? Because we could also do 499999999. So either do both of them, or maybe always choose the one that terminates. And so now what Cantor's diagonalization argument is, form a new number, but look at all these diagonal numbers and modify them. And that will give you a new number that's not on the list. And so one possibility is, whatever number I have here, choose a different number. If the number is not a 5, make it a 5. If it's a 5, make it a 4. Right? So you form a new number x, well, we'll call the new number maybe y, where yn is equal to 5 if xnn does not equal 5, and it's 2 if xn equals 5. So this is a new number that's not in our sequence. Okay? And it will show that it's going to differ. Right? There may be some issue if I have a decimal that repeats. Okay? But I should be okay because I'm using 2's here and not all 9's. Okay? I can't simplify all 2's. Right? So this is a new number on our list. The assumption that we could enumerate all the numbers, that we could put them into one-to-one correspondence with the integers, that's false. So there are sets that are uncountable. If you continue in mathematics, if you take a class like measure theory, you learn that there's different ways of talking about sizes of infinity. There's the measure theoretic sense, there's the topological sense. You can have sets with uncountably many numbers that still have length 0. The Cantor set is a wonderful example of that. Okay? Anybody know the longest song in the English language?
Song?
Yes, the longest song to sing.
A never-ending one.
How does that go?
No one knows. Or the gets on everybody's nerves. Everybody's nerves.
So I need some notation. So the rational numbers, the integers, the natural numbers, they all have the same cardinality. And we use Hebrew letters. That's an aleph not. Okay? We know that the size of the rationals, or the size of the natural numbers, is strictly smaller than the size of the reals. That's what Cantor just proved. It turns out that the size of the reals is 2 raised to the aleph naught. And the way you can view this is, if I'm looking at my decimal expansions, let's do everything base 2. I have 2 possibilities at each digit. I have a 0, I have a 1. And that's where this comes from. Another way of looking at it is, if I have n objects, how many subsets do I have? I have 2 to the n subsets. So whenever I do a power set, the number of elements in the power set is 2 to the number of elements in the set, because each element you either take or don't take. If I want to think about the real numbers, for each decimal digit, I have a 1, I have a 0. We know these numbers are different infinities. The question is, are they adjacent infinities, or is there something else between them? This is the continuum hypothesis. So again, how many of you have heard of the continuum hypothesis? Excellent. One of the purposes of this class is to use these math problems as jumping points to show you good mathematics. So aleph 1 is the next largest infinity. We have the cardinality of the reals. What is the relationship between them? So another way of saying this, is there an infinite set which is strictly larger than the rationals? I can't put it into one-to-one correspondence with the rationals, but it's strictly smaller than the reals.
The irrationals?
Well, the irrationals I can put into one-to-one correspondence with the reals because the rationals are countable insignificant. So what do you think the relationship should be between these? I have less than, equal, greater than. One of them is absurd. Which is the absurdity? Yeah, this cannot be greater than that. It's a subset. So it's either equal to or less than. Which do you think?
Less than.
Less than. Anybody else have any other views? Only one other possible view. Equal. The answer is?
Equal.
Whatever you want. It is independent of the other axioms of set theory. If you look at the standard axioms of set theory, that is not enough information to determine the relationship between these numbers. You can assume, it's more than you don't know. You can either assume that they are equal, and that will be consistent. So if set theory was consistent before, adding the assumption that these are equal will still be consistent. If set theory was consistent before, adding the assumption that they are not equal will also be consistent. It is independent of the other axioms of set theory. The final proof of this, going back to Gödel, was finished by Paul Cohen in the 1960s. He is one of my mathematical grandfathers. And so what made his name was he was the one who developed a concept called forcing in logic to finish the proof that this is independent of the rest of mathematics. And this leads to the longest song in the English language. Aleph not bottles of beer on the wall. How does it go? Aleph not bottles of beer. Take one down, pass it around. Aleph not bottles of beer on the wall. It's amazing how long I was able to get my kids to sing that. Yes. No, that's not a joke. My kids actually really did sing this for quite a while. When they went through periods where they would only listen to one song. And I think we set the record when Cam was young for the most consecutive listens to Barbara Ann by the Beach Boys. Eventually we got to the point where Liz and I were allowed to choose other songs from the Beach Boy album that had Barbara Ann. But that was it. All right, so this is a quick view of countable and uncountable. Some cool facts you should know. If you have two countable sets, their union is countable. So C means countable. Countable union countable is countable. Countable intersects countable is at most countable. countable times countable is countable. So imagine here's your first one, here's your second one, here's your third one. It's the same as what we did for the rationals. You can go through the sets diagonally like this. So a countable union of countably many sets, countable times countable, these are all countable. Okay? Any questions on countable versus uncountable? All right, so what I want to do now is I want to do 3 problems involving countable and uncountable. So number 1, you have a sequence of positive terms. If have uncountably many, then the sum is plus infinity. So there is no way to have an uncountable sum of positive numbers being finite. As soon as you see something like this, you should change one of the assumptions and ask, is it still true? What assumption should I try to change? Okay, so is it possible to have a countable sum of positive terms being finite? So somebody give me a countable sum of positive terms that's finite.
Positive.
1 over 2 to the I. So note, false for countable sums. I could do 1 over 2 to the I. I could do 1 over I squared, although that has implications in complex analysis, so all I did is n squared. So here's 2 examples. Infinitely many terms. If I sum them, it's going to be finite. There is something very different about uncountably many terms. There is no way to have uncountably many positive terms summed to a finite number. All right, so the question is, how do we prove this? What should we use? It's wrong, but someone should still say it.
Induction.
Yes, it's wrong, but it should still be said, right? You know, our first thought should be induction. We're actually going to use something very similar to the pigeonhole principle. Oh. Okay, so how do we want to use the pigeonhole principle?
We want to decide our pigeons and our buckets.
Okay, so let's try to do this with the pigeonhole principle. What should our pigeons be? What are the pigeons? The sequence itself. Terms in sequence. You know, I'm not supposed to say it's obvious as a mathematician, but it's obvious, right? Whenever you have these problems, your pigeons are almost always the sequence you're given. The difficulty is the boxes. Okay? So, what should we choose for the boxes? For problems like this, it's sometimes nice to make simpler assumptions. So, boxes. We can assume all terms are less than or equal to 1. Why can I assume all terms are at most 1? Yes?
Because if they're not, like, if that's not true, like, limiting it that way, if it's true for that small group, it's going to be true for...
Yeah, just take any term that's greater than 1 and replace it with 1. You can only decrease the possible sum. So a lot of times in problems like this, it's not so bad to make some simplifying assumptions. Try looking at some special cases. And it turns out that if you can study and understand those special cases, you can often understand the entire thing. I might as well assume all my numbers are at least 1, because if anything is greater than 1, it only helps. So I now need to have my boxes. This is the difficulty. But the boxes are actually, they've got to somehow use the fact that I have uncountably many objects. How many boxes do I want to have? I want to have countably many boxes. So if I have countably many boxes and uncountably many pigeons, right? It's a little strange. So I load I load uncountably many pigeons into my pigeon gun, and I shoot into countably many boxes. One of the boxes must contain uncountably many pigeons. Otherwise, because countable cross countable is countable, every box having countably many would just mean I have countably many numbers total. I have uncountably many. So any collection of countably many boxes will imply that one box has uncountably many objects. If we go back to 1 over 2 to the n, or 1 over n squared, when I try to put my boxes in, somehow I'm going to be in a situation where I'll only have finitely many objects in each box. And that's why the sum is not going to be forced to diverge. So any thoughts as to what my box should be? I want to have a box so that if I have uncountably many things in it, it's going to diverge. Yes?
How about the intervals from 1 over 2 to the n plus 1 to 1 over 2 to the n, where n goes from 0 to infinity?
Yeah, but I can do it a little bit simpler than that. I can just do 1 over n plus 1 to 1 over n. These are my boxes. So the first box goes from 1/2 to 1. The second box goes from 1/3 to 1/2, 1/4 to 1/3. I have countably many boxes. I have uncountably many pigeons. One of these boxes gets infinitely many terms of my sequence. Well, if you get infinitely many terms of the sequence, if it's in this box, every term is at least 1 over n plus 1. And so what must be true about the sum? So each box is bounded from below if uncountably many in the box 1 over n plus 1, 1 over n, sum is infinite. And we're done. So this is a really nice application of countable, uncountable, and the pigeonhole principle. The difficulty is finding the correct notion of boxes. And that's why I think this is a really good topic to do right after doing the pigeonhole principle. So again, the difficulty is figuring out what the boxes are. Now that we have this, let's go back and let's look at the sequence that converged. If I try to put these terms into these boxes, well, if I look at 1 over 2 to the n, most of these boxes will be empty. And some boxes will have one element. Well, if you have a box with just one element, that's not going to be enough to show that the sum diverges. What if I take 1 over n squared? As I start putting it into boxes like this, most of the boxes will be empty. A couple of the boxes will have one element. What if I took 1 over square root of n? What would happen if I took 1 over square root of n as my sequence? Yeah, not only will every box be filled, but as you go further down, you start getting more and more, you get more and more elements in the boxes. So you'll get some boxes that are going to start to have more and more elements. And that's, yes?
This might be a technicality, but how do we know the sum of uncountably many of those things in that box?
Well, everything in the box is at least 1 over n plus 1. I have infinitely many things. Even if I only take countably many of them, even if I just take a subset of them, it has to diverge.
I think the reason why I'm asking is like, because isn't by technicality that what we're trying to show?
But here now, we're trying to show it for an uncountably many positive numbers. Here I have uncountably many numbers that have at least 1 over n plus 1. If I have uncountably many that are at least 1 over n plus 1, I have countably many that are at least 1 over n plus 1. And I know that sums to infinity. So we are okay with something like that. All right, so the difficulty here was that if I took 1 over square root of n, this sum actually diverges. So that would not be a counterexample. And when I start putting it in here, in that case, it turns out I get a lot of elements in some boxes. But I only have finitely many elements in each box. It's not clear what happens. I have to roll up my sleeves and do some detailed analysis. Okay? But if I have uncountably many terms, then I know one of the boxes has to have countably many objects. In fact, one of the boxes has to have uncountably many objects. So countably many things going into countably many boxes, that does not imply one box has countably many things. uncountably many things going into countably many boxes does. All right, I want to make sure we get to the fun problem. So what I'm going to do is the following. I'm going to just state a problem for you to do maybe at home. So choose infinitely many disks with positive radius assume they're distinct, empty intersections. Prove only have at most countably many. Okay, so this is the problem. I have infinitely many disks, each has a positive radius, and I assume that no disk intersects any other disk. Is there a way to put down uncountably many disks such that this is true? And I'm telling you the answer is no. Okay? So see if you can prove that. Okay, everybody understand the problem? What's the largest radius? What's the largest radius? What can you assume the largest radius is? Yes? 1. Or a half, or a fourth, whatever. You can assume that the radii are bounded. Why? Well, just shrink the disks if necessary. Right? It can only make things harder if the disks are smaller. So if you want, there's no loss in generality in assuming that the disks have radii at most 1. Okay? This is a really good mindset to get into for these problems. I might as well assume my disks are small. All right. Are you ready for the problem? And Kayla had told me that she was going to let me bring her magic wand today, but I realized I forgot to take her magic wand. So I do apologize. Bless you. Bless you. So, do you want to be good or evil? Evil.
Good.
I heard evil first, okay? First loud voice wins. Look, he's evil. He spoke first, okay? You're too good. You were polite. All right, evil. We have a magic wand or sword. We hit the plane and we kill, if you want, brutally, all points an irrational distance away. And only those points. Is this sufficiently evil for you?
Yes.
Okay. Now, question?
All points in a rational distance from like a fixed point in the plane?
From where you tap.
Okay.
You hit the plane at a point,
Got it.
and everything that's an irrational distance from that point is killed. However, it's only those points. So imagine you know where this evil warlord is going to tap. What do? You move to a rational distance. All right? So I did forget the magic wand, but I did remember the sword from Cam and Kayla, okay? Okay, so you tap here, and then the only thing that's, and again, I'm not going to draw every possible circle of rational radius. That would take a little bit too long. These are the points that are safe. How do you feel, evil warlord? But the people who don't believe in your majesty are hiding on these rational rings. What do you do? Yes. I'm sorry, I probably shouldn't be doing this. Yes.
I've hit a point that's irrational. That way, if people are on irrationals, insulate them.
So rephrase, what do you do? So you've tapped here. People are safe on these rational rings, but they can't move onto a place that's dead, or they will die. What do you do now? So we will assume that you want to kill everyone. They don't believe in you, right? Yes?
Or just tap on one of the rationals and see how much you get.
Well, let's do it a little bit more gently. Let's tap somewhere else. So we tap here. Unfortunately, notice that there are some places that are safe. So here is the question. And I'll ask them in level of difficulty. Question 1. Can we do uncountably many taps and kill the entire plane? This one shouldn't be that hard. What's the answer?
Yeah.
Yes. How do we do it? Tap every point. Great. Now, unfortunately, this could take a little bit too much time for our evil warlord. Question 2. Can we do it with countably many taps? And actually, I'm going to change it a little bit. I'm going to call this question Aleph naught. And so as not to show where I view the continuum hypothesis, I'll call this question 2 sub Aleph naught. What do you think question 5 will be? 5 taps. Question 4, question 3, question 2, question 1. All right, question 1, how do we vote? No. Question 2. No. No matter what 2 points you tap in the plane, draw the line connecting them. And now all we need to do is choose a circle of rational radius that's at least larger than half the distance. And if I draw a circle with rational radius here, the same circle like this, that'll give me 2 points that survive. So we know you need at least 3 taps. And we know uncountably many taps is sufficient. So we want to narrow it down somewhere between 3 and uncountably many. All right? Let's try to go from above downward. Do you think we can do it with countably many taps?
Yes.
Okay, how would we do with countably many taps? So how would we do with countably many taps? Yes?
I'm thinking if you started labeling your intersection points, and
Good.
then you did something there.
So how many intersection points do I have of the of the countably many circles here and the countably many circles here?
Countably many.
Countably many. What is the maximum number of times 2 distinct circles can intersect? 2. So each pair of circles intersects at most twice. Right? So for each circle here, I have countably many circles here. Each one gives me at most 2 more points. I have countably many points of intersection. So all I have to do is do taps that are irrational distances from each one of these. So I can do this in countably many. Yes. After 2 taps, at most, countably many points are left. All right, so we're making progress. Now the evil warlord can kill the entire realm with countably many taps. But the evil warlord may have other things to do and may not want to spend countably many iterations tapping. How low do you think we can go? How many? Have you ever seen the game show Name That Tune? They play some music and I can name that tune in 5 notes, I can name that tune in 4 notes, name that tune. Give me a number. Somewhere between 3 and the cardinality of the integers. Who thinks we can do it with 2014 taps? Wow, this much faith in your professor. This is sad. So let's think about what's going on. We have only countably many points. Okay? We need to find one special place to tap, maybe, to kill every single point. How would we do that? Yes?
How many points it's like an irrational distance away from both?
But it could be an irrational distance from these, but maybe a rational distance from here. So maybe I have, yes?
Oh, those two safe points, they're a rational distance from each other, right?
We don't know that.
You don't know that for sure.
But remember, we have lots of different points. Yes?
Well, I'm not sure, but for any 3 points, you can draw a circle between them.
Mm-hmm.
You could make the radius be at a irrational distance.
Good, that would allow me to kill 3 points, but I have uncountably many points to kill. And this is just too slow. This is too slow. Okay, it's a little bit more efficient, but it's still infinitely off, and I want to kill faster. And again, the nicer way to phrase this problem is, you're trying to heal the planet. And you're trying to undo the damage that was done, and every time you tap, you restore vegetation. Okay? So if you would prefer to think of it that way, how many points are a rational distance from this point? Well, so let's think.
Are a rational distance though? Right here.
Okay, let's do an irrational distance from this. How many points are there? Countably many. Uncountably many. Right. Almost every point is an irrational distance away. I have countably many points. So one way to go is maybe let's look at, oh wait, most of you did not take my linear programming class at 10 o'clock. We actually had something very similar to this. Damn. It was such a beautifully prepared lecture. Okay, so if I look at each of these points, I have countably many points. How many points are a rational distance from this? I have countably many rings. And in some sense, what's the measure of those rings? This is now getting us into measure theory. Each of those rings maybe has measure 0. I put them all together countably many times. Maybe I can somehow try to make an argument. So the question is, I want to try to find a way to say there's got to be one point that's an irrational distance away. I want to find a point that's a rational distance from both of these, maybe. So I'll leave this to you to ponder, is can you find a third point that will work? Where if you tap here, you will kill all the remaining points. So one way is to basically just say, well, look, maybe I can somehow find boxes in such a way that if I tap in a special place, I will be fine. Another way to do this problem is to tell you where to tap. If I give you 3 points to tap, and you kill all the points with those 3 taps, we're done. So let's try to think of it as this approach. Where should our first tap be? Look, the evil overload is tapping. Okay, we got to go faster. Where should our first tap be? 0, 0. Why is our first tap at 0, 0? Why not? Make it easy. So we tap at 0, 0. Okay. And so now, again, not drawn to scale. So now, if any point xy survives, so if xy is alive, that implies x squared plus y squared is rational. I actually know more than x squared plus y squared is rational. What do I know? So I know a little bit more than just x squared plus y squared is rational. So what does it mean if I survive? What do you know about my point? So what's true about a point that survives? This is by definition. It's a rational distance. So I know more than just x squared plus y squared is rational. I know the square root of x squared plus y squared is rational. I'm going to forget some information. This is actually enough to do it. So my first tap is 0, 0. I kill every point except those that are a rational distance away. I'm actually going to allow myself to keep not just those, but the points whose distance squared is a rational number. So the evil warlord has a little bit of a cold. He's not quite as powerful. I'm not going to make a difference. Where should my next tap be? So let's choose an irrational distance away. Okay? It seems reasonable to put in an irrational number. What irrational number should we choose?
Pi.
No!
Sorry. 0, 1 over,
Square root of 2. Why should we choose square root of 2?
We know it's irrational.
I'm sorry?
We know it's irrational.
I know many things are rational.
Why couldn't we choose pi?
Pi is much harder to work with, and we'll see in a moment why pi is bad.
Because when we square it, it'll be 2.
When we square it, it's going to be 2, and that's actually going to help us. Root 2 is also very simple. So here's the point square root of 2, 0. And now, imagine my point xy is still alive. So now, if xy is still alive, that implies x minus root 2 squared plus y squared is rational. So we get x squared minus 2 root 2x plus 2 plus y squared is rational. And now what can we deduce? I'm sorry? The square root of what?
No.
What can we deduce?
X is irrational.
How irrational? We can quantify its irrationality.
It's a power square.
It's got to be a rational multiple of square root of 2. Look, we know x squared plus y squared is rational. We know x squared minus 2 root 2x plus 2 plus y squared is rational. So if I subtract this from this, and then I subtract 2, I get negative 2 root 2x is rational. So I get root 2x has to be rational. So the only way a point xy can survive is if root 2x is rational. Okay? This is why I wanted to do square root of 2 and not pi. Because I'm crucially using now that when I square the square root of 2, I get 2. And I want to start combining these. The idea is, well, if I survive after 2 taps, I've got to be in a very special form. Okay? Well, we now need to tap again. Where should we tap?
Root 2, 0.
We just tapped at root 2, 0.
Means 0 root 2.
So we could do 0 root 2. And if we do 0 root 2, we're going to start getting things about y.
Root 2, root 2.
We could do root 2, root 2. But if we do root 2, root 2, we get the same, well, now we've got this combination. So by tapping at root 2, we got root 2x was rational.
How about root 3, 2?
So if we try root 3, 2, say root 3, 0, a similar argument gets root 3x is rational. And now what do we know? So does everyone agree that if we tap at root 3, 0, all we do is replace the 2's with 3's, and we would get root 3, we would get negative 2 root 3x is rational, so we would get square root of 3 times x is rational. Is everybody comfortable with that? So we know root 2x is rational, we know root 3x is rational. What can we deduce? What do we get? Okay, well, how is this a contradiction?
X couldn't have had root 3 in the denominator. Or like root 2x.
So if I take the ratio, if I've got root 2x equals a over b, and I've got root 3x equals c over d, then I would get the square root of 2/3 is ad over bc. And we've just shown the square root of 2/3 is rational. Contradiction. Does this finish the job? So if I have any points that are left, are there any possibilities for the x-coordinate? No. What about the y-coordinate? Do we know any information about the y-coordinate? Do we care at all about the y? Yes.
Well, I think since they're circles, the y coordinates are covered. I don't think we care about them.
We don't care about them because look, if I have a point that's alive, it's got to have some x-coordinate and some y-coordinate to be alive, right? By tapping at 0, 0, we know x squared plus y squared is rational. By tapping at root 2, 0, we know the x-coordinate is a rational multiple of root 2. By tapping at root 3, 0, we know the x-coordinate is a rational multiple of root 3. There are no x-coordinates that are rational multiples of root 2 and root 3, right? Is there any x-coordinate that is a rational multiple of root 2 and root 3? Ooh, what could it be? I'm sorry?
Oh, no.
There's only 0. Oh, no. Maybe x equals 0. So the only possibility that's left is x equals 0. And now the question is there any rational number on here that's a rational distance from all of these? So that's what we have to prove now. Or we could play a very similar game. Notice that we've killed the origin. The origin survived the very first time we tapped, but when we tapped at root 2, 0, we killed the origin. Let's imagine y, 0, y is alive. We know y has to be rational. We know y minus square root of 2 squared has to be rational. And we know y minus the square root of 3 has to be rational squared. So this gives us y squared is rational. This gives us y squared minus 2 root 2y. Oh, I'm sorry. No, I'm sorry. No, I'm sorry. Sorry, this one gives us, that it's going to be y squared plus 2 square roots is rational. And this will give us y squared plus 3 square root is rational. So the question is this enough to get that y can't exist? So what I'm going to do is we've run out of time. Worst case scenario, we've shown after 3 taps, the only thing that's left is on the y-axis. How many taps would it take us to make sure we kill everything? Because all that's left is things that are rational distance, if we just choose a rational number. So we can clearly do 4 taps. So the question is, can you do it in 3? So we haven't solved the problem, so I will leave this as an exercise for you to think about. Can you do it with 3 taps? Can you do it in an explicit way by telling me where? Yes, we can actually make all of this explicit. If I just tap randomly at 3 places or 4 places, will that work? Okay,